When we look at Earth today, the land beneath our feet may seem solid, unmoving, eternal. Mountains rise in the distance, rivers carve their valleys, and continents feel vast and immovable. Yet beneath this illusion of permanence lies a truth far stranger and more dynamic. Earth's surface is restless. Continents are not fixed but drifting, colliding, and breaking apart in slow, patient cycles that span hundreds of millions of years. This dance of movement has shaped our planet's climate, its oceans, and even the history of life itself. At the heart of this story are the supercontinents, immense landmasses in which most of Earth's continents fused into single giants. Their rise and fall are among the greatest rhythms of planetary history, unfolding not in years or centuries, but in spans so vast they challenge human imagination. Each supercontinent has had its own life cycle, born from drifting plates, united by collisions, torn apart by rifts, and remembered in the rocks that remain. Imagine Earth's continents as rafts floating on a deep, slow-moving sea of rock. Beneath the surface, heat rises from the planet's interior, driving convection currents that push and pull the plates above. Over millions of years, this motion gathers continents into clusters. Mountains rise where they collide, oceans shrink as land masses close in, and eventually, the world's land comes together in one mighty supercontinent. But the cycle never ends. Tectonic forces eventually pull these giants apart, opening new oceans, reshaping climates, and setting the stage for new cycles of unification and separation. This cycle is not just geology. It is the backdrop against which life's greatest transformations have unfolded. When continents come together, they change ocean currents, alter weather patterns, and create vast inland environments. Life adapts, struggles, and sometimes flourishes in these new conditions. When continents break apart, new coastlines form. Shallow seas expand, and ecosystems bloom with fresh diversity. From the earliest microbes to the rise of humans, the pulse of supercontinents has guided evolution's path. To grasp the enormity of this story, consider time itself. The human lifespan measured in decades is a blink. Civilizations rise and fall in thousands of years, but supercontinents are measured in hundreds of millions. In the span of one supercontinent cycle, entire species rise, thrive, and vanish, while the continents themselves continue their slow march. It is a scale of time that feels almost eternal, yet it is in motion always. Geologists believe that at least 7 supercontinents have formed and broken apart over Earth's 4.5 billion year history. Some are names few have heard: Valbara, Kenorland, Nunes, or Columbia. Others, like Rodinia and Gondwana, loom larger in scientific memory. And one, Pangaea, is a household name, the great supercontinent that existed just 300 million years ago, when dinosaurs had yet to dominate the Earth. These vast landmasses are gone, but their fingerprints remain in the rocks, in mountain belts that once formed at their seams, and in the minerals that tell stories of ancient oceans now vanished. As we move through this journey, we will see how each supercontinent shaped not only the land, but the entire Earth system. Some stabilized climate for long stretches, creating what scientists call the boring billion, when evolution advanced slowly but steadily. Others triggered extreme shifts, such as snowball Earth, when glaciers may have reached the equator. Each rise and fall reshaped life's possibilities, offering challenges and opportunities in equal measure. There is also a poetic rhythm in this endless cycle. The continents gather, drift apart, and gather again. Like a slow breath the planet takes across deep time. This cycle has no beginning and no end, only transformation. The Earth you walk upon today is not the same as it was millions of years ago, nor will it remain the same millions of years into the future. Already, scientists can trace the direction of today's drifting continents, predicting that one day, long after humanity, another supercontinent will rise. As you let your thoughts quiet, imagine the Earth as seen from space, not just today, but across billions of years. See the continents slowly drifting like pieces of a puzzle, merging into vast supercontinents, then pulling apart again. Imagine oceans closing, mountains rising, glaciers advancing, forests spreading, deserts forming, all under the steady rhythm of tectonic motion. It is a meditation on time itself, a reminder that change is constant, even when it is too slow for us to see. The rise and fall of supercontinents is not only a scientific story, but a deeply human one. for in understanding them, we understand our place in the planet's grand design. The ground beneath us is not fixed but part of a living system, one that connects us to the earliest forms of life and to the future worlds yet to come. This is the story we will explore: the creation and destruction of Earth's greatest land masses and how they shaped oceans, climate, and life, from the first supercontinent Valbara to the familiar Pangaea and into the predictions of what lies ahead. We will journey across billions of years, and in doing so, we will see that the Earth's surface, though restless and shifting, holds a rhythm as steady and eternal as the tides. The term supercontinent sounds dramatic, and rightly so. It refers to a time when most, or nearly all, of Earth's landmasses joined together to form a single, gigantic continent. Imagine a world where there are no separate North or South Americas, no scattered islands of Asia, Africa, or Europe, only one vast land stretching across the surface of the Earth. This is the essence of a supercontinent, and understanding it begins with knowing how Earth's crust works. Earth's outer shell, called the lithosphere, is not one unbroken surface. Instead, it is made up of about a dozen large pieces known as tectonic plates. These plates float on the softer, partially molten layer beneath, called the basonosthenosphere. The plates are always moving, though at speeds of only a few centimeters per year, about the rate at which your fingernails grow. Over millions of years, however, these small movements accumulate into vast changes. Oceans open and close, mountains rise and erode, and continents drift across the globe. Supercontinents are the natural outcome of this process. As plates move, they can gather continents together into massive clusters. Eventually, nearly all the world's land is joined into one giant landmass. Over time, internal stresses, heat from Earth's mantle, and the pull of gravity cause these giants to crack and split apart, forming new oceans between drifting pieces. The process repeats over and over in what scientists call the supercontinent cycle. One of the fascinating aspects of supercontinents is that they are not permanent. Each one has a life cycle lasting hundreds of millions of years. They form, they endure, and then they fragment. The cycle is thought to occur roughly every 400 to 600 million years. By studying the rocks, minerals, and fossils left behind, geologists have pieced together evidence of at least 7 major supercontinents in Earth's history. These include Valbara, Canorland, Columbia or Nuna, Rodinia, Gondwana, and the most famous Pangaea. So how do scientists actually know supercontinents existed, given that they broke apart long before humans appeared? The answer lies in his geological fingerprints. Mountain ranges, for example, often form where continents collide. The Appalachian Mountains in North America, the Caledonian Mountains in Europe, and the Atlas Mountains in Africa all share geological features that suggest they were once part of the same collision zone during Pangaea's formation. Similarly, ancient rock formations across different continents often contain the same minerals and fossils, revealing that those regions were once connected. Another key clue comes from paleomagnetism. When volcanic rocks solidify, tiny magnetic minerals inside them align with Earth's magnetic field. By studying the orientation of these minerals in ancient rocks, scientists can reconstruct the latitude at which the rock formed. These records allow geologists to trace where continents once sat on the globe, showing how they moved over time and when they joined together. Supercontinents are not just geological curiosities, they have profound impacts on Earth's environment and life. When continents cluster together, they create vast inland regions far from the moderating influence of oceans. These interiors can become arid deserts, while the coastlines experience different weather patterns. Ocean currents are altered too, changing global climate systems. During Pangaea's time, for example, much of the interior of the continent was dry and hot, while monsoons shaped the coastal regions. Life is also deeply influenced by supercontinent cycles. When continents collide, shallow seas shrink, ecosystems are disrupted, and species must adapt or perish. At the same time, the splitting of a supercontinent creates new coastlines and shallow marine environments, which often leads to bursts of biodiversity. Many scientists believe that the breakup of supercontinents has triggered evolutionary innovations by creating new ecological opportunities. It is worth noting that not all supercontinents are alike. Some were relatively short-lived, forming and breaking apart within a few 100 million years. Others endured longer, providing stable conditions for life. Each one had unique characteristics, shaped by the arrangement of land and sea, the chemistry of the atmosphere, and the activity of Earth's interior. The study of supercontinents is still a young science. Much of what we know comes from piecing together fragments of rock scattered across today's continents. It is like assembling a giant puzzle when most of the pieces are missing or weathered. New discoveries, whether in ancient mountain belts, deep sea sediments, or microscopic crystals, continue to refine our picture of how supercontinents formed and how they shaped Earth's history. To put the concept into perspective, imagine standing on Earth during the time of Pangaea, about 300 million years ago. You could, in theory, walk from what is now modern-day Florida to what is now Siberia without ever crossing an ocean. The vast interior might stretch for thousands of kilometers, barren and dry, while the edges teemed with lush forests and swamps. The world would look familiar in some ways: mountains, rivers, deserts, but utterly alien in its scale and arrangement. As you let your mind drift, picture the Earth not as it is today, but as a world of shifting puzzles. Continents drift slowly, drawn together by invisible forces, until they fuse into a single, massive supercontinent. For millions of years, this landmass dominates, shaping climate, life, and oceans. Then, cracks form, rifts open, and the landmass breaks apart, scattering pieces across the globe once again. This is the heartbeat of Earth, a rhythm as old as the planet itself. Understanding supercontinents is more than an exercise in geology. It is a way of seeing Earth as alive, dynamic, and ever-changing. The continents beneath our feet are not fixed. They are participants in a grand cycle that has been running for billions of years. By studying supercontinents, we learn not just about rocks and land, but about the conditions that made Earth habitable and allowed life to flourish. In the next chapter, we will explore the very first supercontinents, how they formed, what they looked like, and what clues remain today. The story begins deep in the past, more than 3 billion years ago, when Earth's surface was still young and life was only beginning to stir. When we think of supercontinents, names like Pangaea often come to mind. But Earth's history of giant landmasses stretches much farther back, into the deep past, when life was only beginning to stir in the oceans. The earliest supercontinents, Valbara and Escanorland, were born more than 2.5 billion years ago. They were different from later giants, smaller in scale, simpler in composition, and part of a planet still finding its rhythm. Yet they represent the first steps in a cycle that continues to this day. Geologists believe the earliest true supercontinent was Valbara, which formed around 3.3 billion years ago. The name comes from combining Kaapvaal in South Africa and a Pilbara in Western Australia, two cratons, ancient fragments of crust that share geological similarities and may once have been joined together. Valbara was not a giant like Pangaea. Earth's crust was still developing, and continental landmasses were relatively small. But for its time, Valbara represented an unprecedented union of continental fragments. It provided the first stable environments where shallow seas, volcanic arcs, and mountain belts could interact in complex ways. The evidence for Valbara's existence comes mainly from ancient rocks. The Pilbara and Kaapvaal cratons contain some of the oldest continental crust on Earth, including rocks more than 3.5 billion years old. Within them, geologists find structures such as greenstone beltspurs, zones of metamorphosed volcanic and sedimentary rocks that suggest tectonic collisions and subduction were already shaping Earth's surface. These belts are strikingly similar in both regions, hinting that they were once connected as part of the same landmass. Valbara's significance goes beyond geology. Around the same time, the earliest evidence of microbial life appears in the rock record. Fossilized stromatolites, layered structures built by microbial mats, are found in both the Pilbara and Kaapvaal cratons. This suggests that the shallow seas around Valbara may have hosted some of the planet's first flourishing ecosystems. Eventually, Valbara broke apart, likely around 2.8 billion years ago. Its fragments drifted apart, carried by tectonic forces. but its existence marks the beginning of Earth's long cycle of continental assembly and breakup, roughly 2.7 billion years ago. After Valbara had fragmented, another supercontinent took shape as Kenorland. Compared to its predecessor, Kenorland was larger and more complex, incorporating multiple cratons from what are now North America, Scandinavia, Siberia, and parts of Africa. Kenorland is significant because it shows how supercontinents were evolving, growing larger, longer lasting, and more influential on Earth's systems. Unlike Valbara, which was relatively small, Kenorland stretched across vast distances and influenced global climate and life in profound ways. Evidence for Kenorland comes from ancient mountain belts and rock formations spread across today's continents. For example, rocks in Canada's Superior Province and in Scandinavia's Karelia region show signs of having been part of the same continental collisions. These ancient mountain belts tell us that cratons, once scattered across the globe, were welded together into a single landmass. Kenorland is also tied to one of the earliest known glaciations in Earth's history, around 2.4 billion years ago. This event, sometimes called the Rodinia glaciation, may have been linked to the breakup of Kenorland. As continents split apart, volcanic activity and changes in carbon dioxide levels may have cooled the planet, triggering widespread ice ages. This was also around the time of the Great Oxygenation Event, when photosynthetic microbes began releasing oxygen into the atmosphere. The breakup of Kenorland may have helped drive these planetary scale shifts by altering weathering, carbon cycles, and nutrient flows. Together, Valbara and Kenorland represent the dawn of the supercontinent cycle. Though smaller and less dramatic than later examples, they reveal that Earth's crust was already behaving in ways similar to today. Drifting plates, colliding cratons, and recycling of oceanic crust into the mantle. These early supercontinents helped stabilize Earth's surface and create environments where life could expand. They also highlight the deep connection between geology and biology. The stability of continental shelves around supercontinents provided shallow seas where photosynthetic microbes could thrive. The breakup of Kenorland may have helped trigger one of the most important transitions in Earth's history, the rise of oxygen in the atmosphere. In this sense, supercontinents were not just landmasses, they were catalysts for planetary transformation. To picture Valbara and Kenorland, imagine standing on a shoreline 2.7 billion years ago. The land is rocky, barren, and lifeless. Plants and animals have not yet evolved. But in the shallow waters, microbial mats spread across tidal flats, building stromatolites. The air is thin and low in oxygen, filled with volcanic gases. On the horizon, volcanoes erupt, adding new land to the growing continent. The sun shines slightly dimmer than today, yet greenhouse gases keep Earth warm enough for liquid water. It is a strange and alien world, yet also familiar. The same forces of plate tectonics that shape our mountains and oceans today were already at work, assembling and breaking apart continents. Valbara and Kenorland may be gone, but they left behind the blueprint for all the supercontinents that followed. As you drift into rest, think of these first great landmasses. Valbara, the pioneer, and Kenorland, the builder. They were Earth's early experiments in continental assembly, setting the stage for billions of years of cycles. Their rocks still whisper of ancient oceans, microbial life, and the restless motions of the planet. In the next chapter, we will move forward in time to explore Columbia's, also known as Nuna, one of Earth's first truly global supercontinents. Larger and longer lasting than its predecessors, Columbia marks a turning point in Earth's continental history. Around 1.8 billion years ago, Earth entered a new phase in its geological story. For the first time, nearly all of the planet's major landmasses gathered together into a single vast continent that stretched across much of the globe. This supercontinent is known as Columbia, or Nuna, and it represents one of the earliest times when Earth truly became a world dominated by a single continental giant. Unlike the smaller and shorter, lived supercontinents that came before it, Columbia was expansive, enduring, and transformative. It shaped the surface of the planet in ways that set the stage for the billion years that followed. The evidence for Columbia's existence comes from rocks scattered across multiple continents today. Geologists studying ancient mountain belts in North America, South America, Siberia, China, and India have found signs that these regions were once linked together. The alignment of ancient faults, the chemistry of rocks, and the dating of minerals all suggest that these fragments once belonged to a single massive landmass. When placed back together like pieces of a puzzle, they form the outline of Columbia, which covered a vast portion of Earth's surface around 1.8 to 1.5 billion years ago. Life during this period was still simple, limited mostly to single-celled organisms, but Columbia provided new opportunities for those microscopic life forms. The shallow seas along its coasts would have created broad environments for photosynthetic microbes to grow, producing oxygen and slowly reshaping Earth's atmosphere. Deep inland, the land itself was likely barren and rocky, perhaps dotted with microbial crusts but devoid of plants, forests, or animals. Still, the presence of a massive, stable supercontinent meant that the carbon and nutrient cycles of the planet operated differently, with weathering of its rocks feeding elements into the oceans for life to use. Columbia also influenced Earth's climate. With such a vast landmass, weather systems would have been altered, producing extreme conditions in some regions and stable climates in others. Large deserts may have stretched across its interior, far from the moderating influence of oceans. Along the coasts, however, monsoons and rainfall patterns may have cycled nutrients into shallow seas, fueling the growth of microbial mats and stromatolites. Though invisible to the eye from afar, these microbial communities were changing the planet forever by releasing oxygen into the air. The assembly of Columbia required colossal geological forces. Cratons, which are the stable cores of continents, were brought together through collisions that formed immense mountain belts. These mountains, now worn down and scattered, once rivaled today's Himalayas in scale. As they eroded, sediments washed into oceans, forming new environments where life could persist. The cycle of uplift and erosion tied to Columbia's formation was one of the earliest examples of the planet's ability to recycle materials on a global scale. Columbia lasted for several 100 million years, longer than its predecessors Valbara and Kenorland. Its stability gave Earth a period of relative calm compared to the constant reshuffling of earlier times. Some scientists believe this stability contributed to what is sometimes called Earth's boring billion, a time between about 1.8 and 0.8 billion years ago, when the planet's surface and atmosphere seemed to change very little compared to other dramatic eras. During this time, oxygen levels rose slowly, climates remained fairly steady, and evolutionary progress in life seemed to stall. Though it may sound dull, this long period of stability may have been crucial, giving Earth the chance to maintain balance and prepare for later bursts of change. Imagining Columbia is to picture a strange and alien Earth. The skies held little oxygen, though they were slowly becoming enriched by microbial photosynthesis. The continents, bare of plants, appeared as vast rocky landscapes under the sun, perhaps streaked with rivers and dotted with shallow inland seas. Along the coasts, mats of microbes lined tidal flats, building layered stromatolites as they grew. In the oceans beyond, simple life forms drifted in currents, largely unaffected by the monumental geological events unfolding on land. Though Columbia eventually broke apart around 1.3 to 1.2 billion years ago, it marked an important milestone. It was the first truly global supercontinent, an experiment in Earth's ongoing cycle of assembly and fragmentation. The landmasses it brought together would later separate and regroup into other supercontinents, including Rodinia and Pangaea. Its legacy lives on in the rocks we see today, scattered across continents but carrying the memory of a time when they were all united as one. As you picture Columbia in your mind, imagine the Earth beneath you not as the familiar patchwork of continents we know, but as a single massive landmass surrounded by endless ocean. Picture barren mountains rising and eroding, rivers carrying minerals to the seas, and microbial mats quietly working in the shallows. It was a quiet world, but one that set the foundation for much of Earth's later history. In the next part of our journey, we will move forward to the time of Rodinia, a supercontinent that followed Columbia and reshaped Earth once again. Rodinia would dominate the planet for hundreds of millions of years and leave its mark not only on geology but on the climate and life itself. Around 1.1 billion years ago, Earth saw the rise of another vast landmass, one that would dominate the surface for hundreds of millions of years. This was Rodinia, one of the most important supercontinents in Earth's history. Unlike the earlier giants, which were smaller and less complex, Rodinia was massive and far more stable. Its assembly involved nearly all of Earth's continental blocks being drawn together through a series of collisions that built great mountain ranges, shaped ocean basins, and altered global climates. It was a turning point, not just in geology but in the development of Earth's biosphere. The name Rodinia comes from a Russian word meaning motherland, a fitting title for a supercontinent that may have been central to the story of life on Earth. Evidence suggests Rodinia began forming about 1.1 billion years ago, when cratons and continental fragments collided and welded together into a single immense landmass. Geologists trace this through belts of ancient rocks, mountain chains and fault zones that stretch today across North America, Greenland, Australia, and parts of Asia. These formations, though eroded and broken apart, are clues that continents now scattered were once linked. Rodinia's sheer size meant it changed how Earth worked. The interior of the continent was likely arid and harsh, far removed from the moderating influence of oceans. Deserts may have stretched for thousands of kilometers, while along its coastlines, shallow seas created wide environments where microbial life flourished. Oxygen levels in the atmosphere were still relatively low compared to today, but they were rising steadily, driven by photosynthetic organisms in those seas. This slow build-up of oxygen set the stage for future biological revolutions, even if the world still seemed quiet by comparison. The formation of Rodinia was not a peaceful process. The collisions that built it created vast mountain ranges, rivaling the Himalayas in scale. These mountains eroded over time, washing sediments into surrounding seas and altering chemical balances in the oceans. Weathering of these mountains also played a role in regulating carbon dioxide levels, influencing climate across the globe. The relationship between land, atmosphere, and ocean grew increasingly complex, showing how supercontinents were not just physical giants but engines of planetary change. During its long existence, Rodinia's stability gave rise to what many scientists call the Boring Billion, a period from about 1.8 to 0.8 billion years ago, when Earth experienced few dramatic shifts in climate or biology. At first glance, it may seem uneventful, but this stability was likely crucial. By maintaining steady conditions, Rodinia created a canvas on which life could continue to evolve slowly, building resilience and laying the groundwork for future leaps forward. It was during this time that eukaryotic cells with nuclei, became more widespread, an essential step toward the eventual rise of multicellular life. Around 750 million years ago, however, Rodinia began to break apart. The tectonic forces that had drawn its cratons together began to reverse, pulling the landmass into fragments once again. This breakup had profound consequences. As Rodinia split, new ocean basins opened, altering global circulation and climate patterns. Some scientists believe this breakup was linked to one of the most extreme climate events in Earth's history, the Snowball Earth episodes, when ice sheets may have stretched from the poles to the equator, turning the planet into a frozen sphere. The breakup of Rodinia may have changed atmospheric carbon levels in ways that triggered these global glaciations. Imagining Rodinia is to picture an Earth both alien and familiar. A vast supercontinent dominates much of the planet, surrounded by immense oceans. Its interior is dry, its coasts lined with microbial mats and shallow seas. The skies are hazy, oxygen still too thin for animals but slowly accumulating. The mountains rise and erode, rivers cut through barren landscapes. And the cycle of geology continues unseen but relentless. To a traveler standing on Rodinia's surface, the world would feel empty of life, yet in the oceans nearby, microscopic organisms were setting the stage for everything that would follow. Rodinia's story reminds us that continents are never fixed. They are born, they grow, they break apart, and in doing so they reshape the entire planet. Rodinia was not the last supercontinent, but it was one of the most important, a motherland of geology that influenced both Earth's climate and the slow, steady path of life. When it finally fragmented, the planet entered a new chapter, one marked by ice, upheaval, and transformation. As you drift deeper into rest, imagine Rodinia stretching across the horizon. Endless rock and desert, seas lapping at its edges, mountains rising against a dimmer sun. It was a quiet but pivotal world, a landmass whose legacy lives on in the rocks beneath our feet and in the oxygen we breathe today. In the next chapter, we will look more closely at the long stretch of stability that followed, an era sometimes called Earth's boring billion, and why this seemingly uneventful period was one of the most important foundations for the planet's future. From about 1.8 billion to 800 million years ago, Earth entered what geologists often call the boring billion. It was a time when the planet seemed unusually stable, both geologically and biologically. Compared to the dramatic upheavals of earlier ages and the explosive changes that would follow, this billion-year stretch was quiet, almost uneventful. But beneath the surface of that quiet, slow processes were at work, laying the foundation for the complexity of life and the dramatic climates yet to come. During this long span, Earth's continents were largely united in Rodinia and remained relatively fixed in their positions. Unlike other periods when continents constantly drifted and collided, forming new supercontinents or tearing them apart, this era brought geological calm. Tectonic activity continued, mountains rose and eroded, and oceans shifted, but overall, the surface of Earth experienced fewer massive transformations. This gave the planet a sense of stillness, one that lasted far longer than most geological chapters. The oceans, too, were stable. They were vast and nutrient-poor, without the constant influx of minerals and elements that come when continents break apart or collide. Without fresh supplies of nutrients, life in the oceans evolved slowly. Photosynthetic microbes continued their steady release of oxygen, but the pace was gradual. Oxygen built up in the atmosphere, though at levels far lower than today, creating an environment where life could survive but not yet thrive in its modern forms. For many years, scientists thought of this billion-year span as uninteresting, a lull in Earth's drama. Yet newer studies suggest it was anything but meaningless. The stability of this period may have been exactly what life needed. In the oceans, eukaryotes, cells with nuclei and greater complexity than the simple prokaryotes that came before, began to spread. These cells were more versatile, capable of forming larger and more specialized structures. Though they did not yet build large ecosystems, their presence was a quiet revolution, setting the stage for multicellular life. At the same time, Earth's atmosphere underwent subtle but important shifts. Oxygen levels rose just enough to alter the chemistry of rocks, oceans, and sediments. These changes created environments where new biological possibilities could emerge. The balance of oxygen and other gases during the boring billion was precarious, but it provided a steady background against which evolution could slowly experiment. Without the chaos of constant upheaval, life had room to refine itself. The geology of this time was equally important. With continents stable and erosion steady, vast deposits of sedimentary rocks formed, locking away carbon and oxygen and helping to stabilize the atmosphere. These rocks are still visible today in cratons around the world, silent records of a time when Earth systems found a long-lasting equilibrium. The supercontinent Rodinia acted as both a stabilizer and a gatekeeper, keeping the planet from swinging wildly between extremes. Though called boring, this billion years contained moments of quiet wonder. The first complex microfossils began to appear, suggesting organisms with more than just simple cell walls. Microbial mats spread across coastlines, building stromatolites that grew layer by layer over centuries. In the oceans, microscopic plankton, like organisms, floated in currents, altering the chemical balance of the seas in ways that scientists are still uncovering. The world may have looked empty to our eyes, but at a microscopic level, it was alive with experiments and complexity. Imagining Earth during the boring billion is to picture a calm planet. The skies are hazy but slowly brightening with oxygen. A vast supercontinent dominates the land, dry and barren, with few signs of change. Along its edges, shallow seas shimmer, dotted with microbial communities. In the oceans beyond, single-celled organisms drift and divide, quietly shaping the future. It is a world of patience, of gradual progress rather than sudden leaps. What makes this period fascinating is not what happened quickly, but what happened slowly. It was during this time that Earth's systems of atmosphere, ocean, and geology found balance. a balance that would one day allow for the explosion of multicellular life. Without the boring billion, the later rise of animals, plants, and complex ecosystems might not have been possible. The calm of this era was not wasted, it was preparation. Eventually, the boring billion came to an end. Rodinia began to break apart, climates grew unstable, and Earth entered an age of ice, upheaval, and transformation. But the quiet billion years before that change provided the stability needed for complexity to take root. The planet had paused, and in that pause, it set the stage for everything to come. As you drift deeper into rest, imagine Earth during this stillness. The seas are vast, the land quiet, the skies calm. Time stretches not in moments but in ages. Nothing seems to happen, yet everything is being prepared. The boring billion was not truly boring at all. It was the foundation of the living world we know today. In the next chapter, we will follow the breakup of Rodinia, a shift that shattered stability and plunged Earth into one of its most extreme transformations, the icy grip of the snowball Earth events. Around 750 million years ago, the long stillness of the boring billion gave way to one of the most dramatic transformations in Earth's history. The great supercontinent of Rodinia, which had stood united for hundreds of millions of years, began to fracture. As rifts tore it apart, new oceans opened, and the once stable balance of the planet was disrupted. The consequences reached far beyond geology. The breakup of Rodinia changed the chemistry of the oceans and atmosphere, and some scientists believe it played a key role in triggering a series of extraordinary climate events. Global ice ages so severe they are known as the snowball Earth episodes. When Rodinia began to break apart, enormous geological forces were at work. Stresses within Earth's crust pulled the landmass in different directions, splitting it into fragments that would drift apart over time. These rifts created new ocean basins, releasing heat and gases from Earth's interior through volcanic activity. The shifting continents altered weather patterns and currents, changing how heat was distributed around the planet. With the stability of Rodinia gone, Earth entered an era of instability, both in its surface and in its climate. The breakup of Rodinia exposed fresh rock surfaces to weathering. As rain fell and rivers carried minerals into the oceans, chemical reactions drew carbon dioxide out of the atmosphere. Carbon dioxide, a greenhouse gas, helps keep Earth warm. With less of it in the air, global temperatures began to drop. Combined with changes in ocean circulation, this cooling may have tipped the planet into an ice age of unprecedented scale. Evidence for these extreme glaciations comes from rocks found on every continent. Layers of glacial deposits, sometimes directly overlain by layers of carbonate rock, suggest that ice once reached near the equator. The presence of dropstones, large rocks carried by glaciers and dropped into fine sediments as icebergs melted, shows that ice sheets extended across oceans, not just land. For many scientists, this points to a time when Earth was encased in ice from pole to pole, a true snowball planet. Living through such an era would have been harsh, but life found ways to endure. Microbes may have survived in thin films of liquid water beneath the ice, in cracks where geothermal heat kept conditions warmer, or near volcanic vents on the seafloor. Photosynthetic organisms could have clung to survival in pockets of open water, or thin layers under the ice where light still penetrated. Though life was limited, these refuges allowed it to persist, waiting for the ice to retreat. The snowball Earth events were not short-lived. They may have lasted millions of years, with ice covering most of the planet. Yet eventually, volcanic activity released carbon dioxide back into the atmosphere, building up over time. With the planet's surface largely frozen, weathering could not remove this carbon dioxide, so it accumulated, intensifying the greenhouse effect. Eventually, global temperatures rose high enough to melt the ice. When the ice sheets receded, they left behind a transformed Earth. The aftermath of these global ice ages was profound. The sudden warming after long cold periods released torrents of meltwater, altered ocean circulation, and flooded the seas with nutrients. These changes may have fueled evolutionary innovation, giving rise to new forms of life that would later explode in diversity during the Cambrian period. Far from being a pause, the snowball Earth events may have acted as catalysts, reshaping both the planet and the biosphere. Imagining Earth during the breakup of Rodinia and the snowball Earth is to picture a planet of extremes. First, the immense supercontinent splintering into fragments, volcanoes roaring along rift zones, and new oceans opening under a dimmer sun. Then, ice spreading across the surface, glaciers grinding over mountains, oceans freezing nearly solid, and the world locked in silence. Finally, the great thaw, with rising seas, stormy skies, and the return of open oceans. It was a time when Earth swung from stability to chaos and back again, a cycle that tested the resilience of life and reshaped the course of evolution. The story of Rodinia's breakup and the snowball Earth reminds us of how closely connected geology and climate truly are. The movement of continents does not just change the map. It can alter the balance of gases in the atmosphere, shift circulation in the oceans, and drive the entire planet into extremes of cold or heat. The breakup of one supercontinent helped trigger events that nearly froze the world, but also helped prepare it for the rise of more complex life. As you rest, imagine drifting across an icy ocean, the stars shining above a frozen planet, silence stretching for millions of years. Beneath the ice, life endures in hidden places, waiting patiently for warmth to return. And when it does, the world will never be the same. In the next chapter, we will follow the rise of Pangaea, a short-lived supercontinent that emerged after Rodinia's breakup, and see how its brief existence helped shape the next stage of Earth's history. After the dramatic breakup of Rodinia and the icy grip of snowball Earth, the stage was set for the rise of another supercontinent, Pangaea. Unlike Rodinia, which endured for hundreds of millions of years, Pangaea's existence was brief, lasting only around 60 million years. Yet in that short span, it played a pivotal role in shaping the Earth of the late Precambrian, influencing oceans, climate, and the conditions under which complex life would begin to emerge. Pangaea formed around 600 million years ago as the fragments of Rodinia drifted and collided once more. Continents reassembled, creating a roughly shaped landmass with its open end facing south. Unlike Rodinia, which had been centered near the equator, Pangaea was oriented closer to the South Pole. This placement gave it different climatic and environmental effects, as ice sheets could form more readily over landmasses near the poles. The arrangement of Pangaea influenced the surrounding oceans. The great superocean Pangaea surrounded it, while interior seaways cut across its land. Ocean currents shifted as continents blocked or redirected the flow of water, altering patterns of heat distribution. These changes, combined with lingering effects of the snowball Earth glaciations, may have driven dramatic swings in climate during this period. Life, too, was entering a period of transformation. The end of the Precambrian, around the time of Pangaea, saw the rise of the Ediacaran biota, the earliest large, complex organisms visible in the fossil record. These strange, soft-bodied creatures bore little resemblance to modern animals. Some looked like fronds or quilted discs lying on the seafloor. Others seemed like ribbed tubes or segmented mats. Their sudden appearance may have been linked to the environmental upheavals of the time, as melting glaciers and shifting oceans delivered new nutrients to the seas. Pangaea's brief lifetime was marked by instability. The same tectonic forces that brought it together soon began to pull it apart again. By around 540 million years ago, the supercontinent had already started to fracture into pieces that would become the continents of Gondwana, Laurentia Baltica, and Siberia. This fragmentation coincided with one of the most significant transitions in Earth's history, the dawn of the Phanerozoic Eon and the Cambrian explosion of life. Geological evidence of Pangaea is harder to piece together than that of Rodinia or later supercontinents like Pangaea. Its short lifespan means that fewer rock sequences preserve its story. Still, by comparing mountain belts, sediment deposits, and paleomagnetic signatures across modern continents, scientists have reconstructed its rough outline and timing. These records reveal a dynamic planet, restless and ever-shifting, where continents are not permanent fixtures but moving puzzle pieces in a much larger cycle. The breakup of Pangaea had lasting consequences. As continents drifted apart, shallow seas spread across their margins, creating new habitats for life. The increased coastline length gave rise to diverse ecosystems where nutrients could concentrate, fostering early animal evolution. The tectonic activity also released fresh nutrients into the oceans, further fueling the biological boom. In many ways, The fragmentation of Pangaea helped set the stage for the extraordinary diversification of life in the Cambrian. From a planetary perspective, Pangaea highlights the transient nature of supercontinents. While they may dominate Earth's surface for millions of years, they are ultimately temporary, held together only until tectonic forces pull them apart again. Each cycle of assembly and breakup not only reshapes geography, but also influences climate, oceans, and life itself. Imagining Earth during the age of Pangaea is to picture a world in transition. Vast glaciers still lingered from earlier ice ages, while new seas opened as land masses shifted. Strange life forms spread across the seafloor, silent and alien. The supercontinent itself was unstable, its brief existence like a bridge between eras, a final act of the Precambrian before the curtain rose on the Cambrian explosion. As you drift into rest, envision the outlines of Pangaea stretching across the globe. Surrounded by endless ocean, imagine the first large organisms swaying gently in shallow seas, precursors of the explosion of life to come. Picture the landmass beginning to crack, drifting toward separation, setting in motion the next great chapter of Earth's story. In the next chapter, we will follow the rise of Gondwana, one of the largest and longest-lived supercontinents in Earth's history, and explore how it shaped both the planet and the path of life. After the short-lived existence of Pangaea, Earth entered the Paleozoic era, and a new supercontinent began to take shape, Gondwana. Unlike Pangaea, which lasted only tens of millions of years, Gondwana endured for hundreds of millions, dominating the southern hemisphere and playing a central role in the story of life, oceans, and climate. Its rise marked one of the most influential chapters in Earth's geological and biological history. Gondwana began forming around 550 million years ago, during the late Precambrian and early Cambrian periods. As Pangaea broke apart several landmasses, what would become South America, Africa, Antarctica, Australia, the Indian subcontinent, and parts of the Middle East, drifted together. By the early Paleozoic, these fragments had sutured into a vast supercontinent, covering much of the southern hemisphere. Gondwana's sheer size made it one of the largest supercontinents ever to exist, spanning from the equator to the polar regions. The climate of Gondwana was varied and dynamic. Its vast interior experienced deserts and dry conditions, while its coasts hosted warm, shallow seas. At times, parts of Gondwana extended over the South Pole, leading to widespread glaciations, especially during the late Ordovician and late Paleozoic ice ages. Glaciers carved deep valleys, left behind distinctive deposits, and influenced sea levels worldwide. These ice ages were not just local events, because Gondwana was so large, its ice sheets had global effects, altering ocean circulation and climate patterns across the entire planet. Oceans surrounding Gondwana teemed with life. The Paleozoic was a time of incredible biological diversification, beginning with the Cambrian explosion. In the shallow seas along Gondwana's margins, trilobites, brachiopods, mollusks, and early corals thrived. Reef systems began to spread, offering habitats for countless species. Over time, fish appeared and diversified, giving rise to jawed vertebrates, ancestors of all modern animals with backbones. Gondwana's coastlines and seas provided some of the most important environments in which life's great evolutionary experiments took place. On land, Gondwana also bore witness to profound changes. Plants first colonized its coasts and riverbanks during the Silurian period, gradually spreading into its interior. These early plants were small and simple, but by the Devonian period, lush forests of ferns, horsetails, and seed plants had emerged. As plants grew larger and spread farther, they transformed the atmosphere, drawing down carbon dioxide and releasing oxygen. This shift contributed to climate cooling and laid the foundation for future animal colonization of land. Animals soon followed. In the late Devonian, amphibians, creatures capable of living both in water and on land, began to appear. They thrived in Gondwana's wetlands and river systems, marking the beginning of vertebrate life on land. By the Carboniferous and Permian periods, reptiles emerged, better adapted to drier conditions. Gondwana was now not only a supercontinent of oceans and forests, but also a stage for the dramatic rise of terrestrial ecosystems. Geological evidence of Gondwana's existence is widespread today, preserved in rocks across modern continents. Mountain belts, such as the Cape Fold Belt in South Africa and the Ellsworth Mountains in Antarctica record the collisions that stitched Gondwana together. Glacial deposits called tillites, found in India, South America, and Africa all match in age and type, proving that these regions were once united under Gondwana's icy grip. Fossils of identical species of plants and animals, found across now distant continents, further confirm their ancient connection. Gondwana's influence was not limited to life and climate, it also shaped the geography of future continents. Over time, it collided with smaller landmasses like Laurentia Baltica and Siberia to help form the later supercontinent of Pangaea. Gondwana's position in the southern hemisphere ensured it played a crucial role in this larger tectonic dance, acting as the anchor around which other landmasses gathered. For all its stability, Gondwana was not eternal. During the Mesozoic era, around 180 million years ago, it began to break apart. As tectonic rifts split it into fragments, the continents we know today, South America, Africa, India, Antarctica, and Australia, began their separate journeys. The legacy of Gondwana remains imprinted in the geography of our planet, a reminder of the long cycles of assembly and breakup that define Earth's history. As you relax, imagine Gondwana in its prime. Picture vast deserts stretching into the distance, forests rising along rivers, glaciers grinding across the southern lands, and shallow seas alive with trilobites and corals. See amphibians crawling from the water for the first time, forests pumping oxygen into the air, and reptiles spreading across dry plains. Gondwana was more than a continent. It was a cradle of transformation, a foundation for the world we live in today. In the next chapter, we will trace how Gondwana eventually joined with other continents to create Earth's most famous supercontinent, Pangaea, a landmass that brought together almost all of Earth's land in one colossal expanse. After hundreds of millions of years, Gondwana, mighty though it was, did not remain alone. During the late Paleozoic, tectonic forces drove continents together, and the result was one of the most iconic supercontinents in Earth's history, Pangaea. Unlike Gondwana, which dominated the southern hemisphere, Pangaea united nearly all the planet's landmasses into one colossal expanse. Its rise reshaped oceans, altered climates, and profoundly influenced the course of life. The assembly of Pangaea began around 335 million years ago, during the Carboniferous period. Gondwana drifted northward, colliding with smaller continents like Laurentia, Baltica, and Siberia. These collisions raised vast mountain ranges, some of which still exist today. The Appalachian Mountains in North America, the Urals in Russia, and ranges in northern Africa all trace their origins to this monumental event. The suturing of continents stitched together an immense landmass stretching from pole to pole, surrounded by a single global ocean, Panthalassa. Pangaea's size made it unique. Covering nearly one-third of Earth's surface, it was the largest supercontinent in the Phanerozoic Eon. Its central regions lay far from the moderating influence of oceans, giving rise to extreme climates. Vast deserts, some of the largest in Earth's history, spread across its interior. Seasonal swings between heat and cold grew severe, and much of Pangaea's heartland may have been inhospitable. Along its coasts, however, shallow seas supported lush ecosystems, forests, and thriving marine life. Life during Pangaea's rise was diverse and dynamic. On land, amphibians and reptiles flourished, filling niches across rivers, swamps, and deserts. The late Carboniferous period saw vast coal forests, dominated by giant ferns, horsetails, and lycopsids, which captured enormous amounts of carbon dioxide and enriched the atmosphere with oxygen. Oxygen levels during this time may have been higher than at any other point in Earth's history, allowing giant insects and arthropods to thrive. Dragonflies with wingspans the size of seagulls, millipedes longer than humans, and other oversized creatures. As the Permian period began, reptiles diversified further, evolving into early synapsids, the ancestors of mammals, and diapsids, the ancestors of modern reptiles and birds. Some synapsids grew into massive predators like Dimetrodon, while others adapted to herbivory, grazing across Pangaea's plains. These evolutionary experiments set the stage for the dominance of reptiles in the Mesozoic era. Marine life also flourished around Pangaea. Coral reefs spread widely, while ammonites, brachiopods, and fish diversified. Coastal ecosystems along Pangaea's vast shorelines provided habitats for countless species, while the open Panthalassic Ocean supported massive currents that distributed heat around the globe. Yet these same oceans could also deliver hardship, as shifting currents and changing climates sometimes led to widespread extinctions. The climate of Pangaea was not static. During its formation, ice ages gripped parts of Gondwana, with glaciers covering large regions of what are now South America, Africa, and India. As the supercontinent stabilized, climates grew warmer and drier, contributing to the spread of deserts. Later, volcanic activity and tectonic shifts influenced atmospheric carbon dioxide, driving further climate fluctuations. Pangaea's vastness magnified these effects, making the supercontinent a swinge for dramatic swings between icehouse and greenhouse conditions. One of the most striking aspects of Pangaea was its role in mass extinction. Around 252 million years ago, near the end of the Permian, Earth experienced the most devastating extinction event in its history, the Permian-Triassic extinction, triggered by massive volcanic eruptions in what is now Siberia. Along with climate shifts and ocean anoxia, this catastrophe wiped out more than 90% of marine species and around 70% of terrestrial species. Pangaea's unified geography may have amplified the disaster, as limited coastlines and shallow seas reduced ecological refuges. Despite this upheaval, Pangaea endured for more than 150 million years. During that time, it shaped evolution, creating a global stage on which new lineages could spread widely. Its vast deserts challenged species to adapt to arid conditions, while its coasts supported rich biodiversity. The rise of dinosaurs in the Triassic period occurred against the backdrop of Pangaea, with these reptiles spreading quickly across the connected land. Eventually, however, the same tectonic forces that assembled Pangaea began to tear it apart. By the early Jurassic, rifts split the landmass, opening new oceans such as the Atlantic. This breakup would reshape the globe yet again, scattering continents into their modern positions. But the legacy of Pangaea remains profound, etched into mountains, fossils, and the very distribution of species alive today. As you drift into calm, imagine standing in the heart of Pangaea. Around you stretch endless deserts, red sands under scorching skies. Along distant coasts, forests rise, and giant dragonflies buzz through the air. Amphibians croak in swampy pools, while reptilian predators prowl the land. The land is vast, harsh, and alive, a supercontinent of extremes. Pangaea was not just a landmass, it was an experiment in planetary scale, shaping the course of life and climate for millions of years. In the next chapter, we will follow the dramatic breakup of Pangaea, exploring how rifts, volcanism, and drifting continents reshaped oceans, climates, and ecosystems, paving the way for the age of dinosaurs. The breakup of Pangaea marked the end of one of Earth's grandest geological experiments and the beginning of a new era of drifting continents and evolving ecosystems. Around 200 million years ago, during the early Jurassic period, tectonic forces began pulling apart the massive landmass, splitting it into smaller continents that would slowly take the shapes we recognize today. This fragmentation set the stage for the Mesozoic era, often called the Age of Dinosaurs, and profoundly altered Earth's climate, oceans, and biodiversity. The process began with rifting. Deep within the mantle, currents of molten rock pushed upward, stretching and thinning the crust. As cracks opened, lava welled up, creating new seafloor. This rifting was accompanied by immense volcanic activity, most notably in what geologists call the Central Atlantic Magmatic Province (KMP). Over a few million years, enormous floods of basalt erupted across what is now eastern North America, western Africa, and parts of Europe and South America. These eruptions released vast amounts of carbon dioxide, driving rapid climate changes. As the Atlantic Ocean began to open, Pangaea split into two major landmasses, Laurasia in the north and Gondwana in the south. Laurasia contained what would become North America, Europe, and Asia, while Gondwana included South America, Africa, Antarctica, Australia, and India. These new continents began to drift apart, carried on the conveyor belts of plate tectonics. The opening of the Atlantic marked the birth of a new ocean, one that would eventually grow into the vast body we know today. The breakup of Pangaea transformed climates worldwide. With smaller continents scattered across latitudes, climates became more varied. Where once vast deserts had dominated Pangaea's interior, new coastlines brought rainfall and moderated temperatures. Ocean currents shifted, redistributing heat and creating more complex weather systems. This fragmentation gave rise to new ecological opportunities, fostering diversification among plants and animals. Life responded dramatically to these changes. The Triassic period, when rifting began, was a time of recovery from the Great Permian-Triassic extinction. As Pangaea split, ecosystems rebounded, and new groups emerged. Among the most successful were the dinosaurs. Their rise coincided with the breakup, and the connected land bridges of early Laurasia and Gondwana allowed them to spread rapidly. Soon, dinosaurs became dominant across the globe, adapting to forests, plains, and coasts. Marine life also flourished during this time. The opening of new seaways expanded shallow marine habitats, where reefs grew and fish diversified. Ammonites and other mollusks thrived, while marine reptiles like ichthyosaurs and plesiosaurs patrolled the seas. The breakup of Pangaea had turned a once limited oceanic system into a patchwork of basins and coastlines, creating diverse environments for evolution. The volcanic eruptions that accompanied Pangaea's breakup had a darker side. The release of greenhouse gases contributed to global warming and ocean acidification. These changes likely played a role in the Triassic-Jurassic extinction event, which cleared the stage for dinosaurs to rise. The interplay of geology and biology was stark. Tectonic rifting not only reshaped continents, but also determined which species survived and flourished. Evidence of this great breakup is visible today. The coastlines of South America and Africa fit together like puzzle pieces, a remnant of their former union. Matching rock formations and fossil records across these continents confirm their shared past. Basalt flows from the Central Atlantic magmatic province still cover vast regions, silent witnesses to the fiery forces that tore Pangaea apart. As the breakup continued into the Cretaceous period, Gondwana itself began to fracture. India broke away and began its rapid journey northward, eventually colliding with Asia to raise the Himalayas. Africa drifted north toward Europe, while South America slid westward, opening the South Atlantic. Australia and Antarctica remained joined for much longer, but eventually parted as well. The world was no longer dominated by a single landmass, but by scattered continents, much like today. The breakup of Pangaea had profound consequences for evolution. Isolated continents became laboratories of biodiversity, each developing unique ecosystems. For example, when South America split from Africa, its animals and plants began to evolve separately, leading to the distinct species found there today. The fragmentation of the supercontinent turned Earth into a mosaic of habitats, encouraging the diversification of life on an unprecedented scale. As you rest, imagine the Earth during this time of transition. Picture Rift Valley splitting the land, lava fountains glowing red under Jurassic skies, and new oceans opening as continents drift apart. See dinosaurs spreading across fresh landscapes, forests growing along new coastlines, and seas filling with life. The breakup of Pangaea was not destruction, but transformation, a shift that reshaped Earth into a world of variety and complexity. In the next chapter, we will follow the scattered fragments of Gondwana as they continued to drift, giving rise to the modern continents of the Southern Hemisphere and shaping the global map we recognize today. As Pangaea fractured, its southern half, Gondwana, underwent one of the most dramatic tectonic journeys in Earth's history. Between 180 and 100 million years ago, Gondwana began to split apart, scattering its fragments across the Southern Hemisphere. From this breakup emerged the continents of South America, Africa, India, Antarctica, and Australia, each drifting into the positions they hold today. This process reshaped oceans, climates, and ecosystems, and it profoundly influenced the evolution of life. The breakup of Gondwana began with rifting in the Jurassic period, around 180 million years ago. Deep fissures opened in the crust, driven by mantle plumes rising from below. Lava flooded across vast areas, leaving behind enormous basalt provinces, much like those formed earlier during Pangaea's breakup. These rifts widened, allowing new oceans to form. The South Atlantic, Indian, and Southern Oceans all trace their origins to this time of separation. The first major split occurred between Africa and South America. Around 140 million years ago, the South Atlantic began to open and the two continents drifted apart. Today, their matching coastlines, like the jigsaw fit of Brazil and West Africa, bear witness to this ancient connection. Fossil records strengthen the case identical species of plants, such as the seed fern Glossopteris, and animals like early reptiles, are found on both continents, proof that they were once united in Gondwana's lush forests. Meanwhile, India embarked on a remarkable journey. Originally part of eastern Gondwana, it broke free around 120 million years ago and began racing northward at extraordinary speeds for a tectonic plate, up to 15 centimeters per year. Its eventual collision with Asia, tens of millions of years later, would uplift the Himalayas, the tallest mountains on Earth. During its voyage, India carried with it unique ecosystems, which later merged with those of Asia, creating dramatic evolutionary consequences. Australia and Antarctica also remained linked for a long time after Gondwana's initial breakup. Their shared fossil evidence, such as marsupials and ancient forests, shows their close connection. Around 85 million years ago, Australia began to separate and drift northward, while Antarctica remained isolated at the South Pole. Once encircled by the Southern Ocean, Antarctica became locked into its icy state, its climate plunging into the deep freeze that defines it today. The breakup of Gondwana dramatically altered ocean circulation. As new seaways opened, currents shifted, redistributing heat across the globe. The South Atlantic began carrying warm waters between hemispheres, while the separation of Australia and Antarctica allowed the Antarctic Circumpolar Current to form, a powerful current that isolated Antarctica and locked it into glaciation. These changes helped shape the climates we recognize in the modern world. Life was profoundly affected by Gondwana's fragmentation. Isolated continents became evolutionary laboratories. South America, cut off for tens of millions of years, developed unique species like giant flightless birds and marsupials. Australia became home to its famous marsupials and monotremes, while Africa nurtured lineages that would eventually lead to elephants, primates, and other iconic species. Antarctica, once forested, gradually froze into a barren ice sheet, preserving evidence of its lush past in fossilized wood and leaf impressions. The ecosystems of Gondwana during its heyday were diverse and vibrant. Before the breakup, vast coal forests stretched across its expanse, providing the basis for much of the coal we mine today. Rivers carried nutrients to shallow seas, where marine reptiles like plesiosaurs swam alongside ammonites and early sharks. Dinosaurs roamed across Gondwana's plains, including the mighty sauropods of South America and Africa, some of the largest creatures ever to walk the earth. Geological clues to Gondwana's story remain abundant. Glacial deposits from the late Paleozoic, identical in age and character, are found across South America, Africa, India, and Australia, confirming their shared history near the South Pole. Mountain belts, such as the Transantarctic Mountains and the Eastern Ghats of India, reveal the sutures where Gondwana's pieces were once joined. Even today, paleomagnetic studies of rocks trace the latitudinal drift of these continents as they move to their modern positions. The breakup of Gondwana reminds us that continents are not permanent. They are travelers, carried slowly but relentlessly by the currents of Earth's mantle. What once was a unified southern supercontinent is now scattered across half the globe, its fragments hosting some of the richest and most distinctive biodiversity on Earth. As you imagine this ancient world, picture Gondwana as a lush, green land stretching from pole to equator, home to giant ferns, primitive forests, and early dinosaurs. Then watch as fissures split its crust, lava fountains burst forth, and oceans flood into the rifts. Picture South America sliding west, Africa drifting east, India racing north, and Antarctica sinking into icy isolation. The breakup of Gondwana was not just geological, it was a turning point that shaped the Earth we know today. In the next chapter, we will shift our gaze northward to Laurasia, the counterpart to Gondwana, and explore how it shaped ecosystems, climates, and the evolutionary story during the age of dinosaurs. As Gondwana began to fragment after the breakup of Pangaea, the southern hemisphere entered a period of dramatic transformation. The once mighty landmass that had stretched across half the globe slowly broke into pieces, each drifting on its own tectonic path. These fragments would eventually become the continents we know today: South America, Africa, Antarctica, Australia, and India. The drifting of Gondwana shaped not only geography, but also climate, ocean circulation, and the evolution of life. The earliest stages of Gondwana's breakup began in the Jurassic, around 180 million years ago. Rifting first separated Africa from South America, opening the South Atlantic Ocean. At the same time, Antarctica began to move away from both Africa and Australia. India, meanwhile, broke free and embarked on a rapid journey northward, one of the fastest tectonic migrations in Earth's history. By the Cretaceous period, Gondwana had ceased to exist as a single entity, replaced by a scattering of drifting continents. Each fragment of Gondwana developed its own unique destiny. South America, splitting from Africa, drifted westward. Its separation opened the Atlantic Ocean and created coastlines that today stretch thousands of kilometers. The continent's isolation allowed unique ecosystems to evolve, from dinosaurs of the Cretaceous to the diverse mammals and birds that came later. Fossils found in Patagonia reveal an astonishing record of Gondwana's creatures, including massive sauropod dinosaurs and early mammals. Africa, once the heart of Gondwana, moved northward. Over millions of years, it drifted closer to Europe, eventually colliding to form the Mediterranean region. This slow-motion crash raised mountain ranges like the Alps and Atlas, reshaping global geography. Africa's journey also influenced ocean currents, as the closure of ancient seas redirected circulation patterns and altered climate worldwide. India's story was perhaps the most dramatic. Breaking from Gondwana around 130 million years ago, it raced north at speeds of up to 15-20 centimeters per year, remarkably fast by geological standards. Its collision with Asia around 50 million years ago uplifted the Himalayas, the tallest mountains on Earth. This event profoundly altered global climate, intensifying monsoons and reshaping atmospheric circulation. The Himalayas remain a living reminder of Gondwana's drifting legacy. Australia and Antarctica remained connected for longer, lingering together until about 45 million years ago. When they finally separated, Antarctica drifted over the South Pole and became isolated by the Antarctic Circumpolar Current. This powerful current, circling the continent without interruption, locked Antarctica into a frozen state, creating the vast ice sheets we see today. Australia, freed from its icy neighbor, drifted northward, gradually warming and developing its unique ecosystems of marsupials and eucalypt forests. The breakup of Gondwana transformed ocean circulation. As new seaways opened, currents shifted, redistributing heat around the globe. The South Atlantic, the Indian Ocean, and later the Southern Ocean all emerged from these tectonic changes. These currents played a crucial role in regulating climate, driving everything from monsoons in Asia to ice growth in Antarctica. Without Gondwana's breakup, Earth's climate system would look entirely different. Life adapted to these shifting landscapes. During the Cretaceous, dinosaurs roamed across the drifting continents, evolving separately in isolation. South America hosted enormous titanosaurs, Africa was home to fearsome predators like Spinosaurus, and Antarctica, even in its warmer past, supported forests and unique dinosaur species. As the continents continued to drift and climates changed, new opportunities arose for plants, mammals, and eventually humans to thrive. Geological evidence of Gondwana's breakup is everywhere today. Matching fossils of plants like Glossopteris, found in South America, Africa, India, Antarctica, and Australia, prove that these continents were once joined. Mountain belts and rock formations, identical across now distant lands, further confirm their shared history. Even the coastlines themselves, like the near-perfect jigsaw fit of South America and Africa, testify to Gondwana's unity and its eventual fragmentation. As you relax, imagine Gondwana breaking apart piece by piece. Picture rift valleys opening, lava flowing as continents split, and new oceans forming in the gaps. See India racing northward, colliding with Asia in a titanic crash. Imagine Antarctica drifting into isolation, its forests giving way to ice, while Australia drifts toward the tropics, sprouting new forests and creatures. The breakup of Gondwana was not sudden, but a slow dance of continents, unfolding over millions of years. In the next chapter, we will explore how Laurasia, the northern counterpart to Gondwana, shaped the northern hemisphere and contributed its own chapters to Earth's story of drifting supercontinents. While Gondwana dominated the southern hemisphere, its northern counterpart, Laurasia, played an equally important role in shaping the Earth story after the breakup of Pangaea. Formed during the late Paleozoic as part of Pangaea's assembly, Laurasia remained a vast northern landmass throughout much of the Mesozoic, composed of what would become North America, Europe, and Asia excluding India. Laurasia influenced climate, ocean circulation, and the spread of life during a critical period of Earth's history. When Pangaea began to rift apart around 200 million years ago, Laurasia separated from Gondwana. At first, the two remained relatively close, joined by the narrowing Tethys Ocean, but as the Atlantic widened, Laurasia became increasingly isolated, developing its own climates and ecosystems. Unlike Gondwana, which was largely positioned in the southern hemisphere, Laurasia sprawled across the equator and into northern latitudes. This placement gave it diverse climates, from tropical coasts to temperate forests and polar regions. During the Jurassic period, Laurasia was a land of lush vegetation and rising reptilian dominance. Warm, humid climates supported forests of conifers, cycads, and ginkgos, providing food and shelter for the growing diversity of dinosaurs. Giant sauropods like Brachiosaurus roamed the plains, while predatory theropods such as Allosaurus hunted them. Along the coasts, shallow seas supported abundant marine life, including ammonites, ichthyosaurs, and plesiosaurs. Laurasia's environments were vibrant, diverse, and teeming with evolutionary innovation. By the Cretaceous period, Laurasia's landscapes had become even more dynamic. Shallow inland seas flooded parts of North America, creating habitats rich in marine reptiles, mosasaurs, and vast schools of fish. In Asia, feathered dinosaurs began to appear, their fossils preserved in remarkable detail in sites like Liaoning, China. These creatures, small and bird-like, marked one of the most important transitions in Earth's history, the evolution of birds from theropod dinosaurs. Laurasia was, in many ways, the cradle of avian evolution. The tectonic evolution of Laurasia was complex. North America slowly drifted westward, colliding with smaller island arcs to form mountain ranges such as the Rockies. Eurasia, meanwhile, was a patchwork of colliding microcontinents and terrains. The ongoing closure of the Tethys Ocean gradually brought Africa closer to Europe and Asia, setting the stage for future mountain building. Throughout this time, subduction zones around Laurasia's edges fueled volcanic arcs, earthquakes, and the creation of new crust. Laurasia also influenced global climate through its geography. Positioned across both equatorial and high latitudes, it helped shape wind and ocean circulation. Seasonal monsoons affected its interior, while its mountain ranges altered rainfall and created deserts. The opening of the North Atlantic Ocean further redistributed heat, laying the foundations for the currents that still regulate climate today. For life, Laurasia provided countless opportunities for diversification. Dinosaurs of every kind flourished across its landscapes: herbivores, predators, flyers, and swimmers. Mammals, though still small and nocturnal during much of the Mesozoic, also diversified quietly in Laurasia's forests and burrows. They would remain in the background until the extinction of the dinosaurs opened new ecological niches. Geological and fossil evidence ties Laurasia's story together. Fossils of similar dinosaurs, plants, and marine organisms are found across North America, Europe, and Asia, reflecting their shared history before the Atlantic grew too wide. Rock formations, mountain belts, and volcanic deposits provide records of the tectonic collisions and rifting events that shaped the landmass. Eventually, Laurasia itself began to fragment. By the late Cretaceous and early Cenozoic, North America and Eurasia had drifted farther apart, separated by the widening Atlantic. India, once part of Gondwana, slammed into Asia around 50 million years ago, uplifting the Himalayas and reshaping climate and circulation on a global scale. Laurasia's legacy lives on in the modern continents of the Northern Hemisphere, their geology and ecosystems still shaped by this ancient union. As you relax, imagine Laurasia and its prime vast forests stretching to the horizon, inland seas glistening under warm skies, and herds of dinosaurs moving across plains. Picture feathered creatures gliding between trees, while great reptiles swam in nearby seas. See volcanoes smoking on distant horizons as continents shifted slowly beneath. Laurasia was not just a landmass, it was a dynamic world, alive with the beginnings of ecosystems that would echo into our present. In the next chapter, we will explore how the drifting continents of Laurasia and Gondwana gradually settled into the familiar shapes of today, creating the modern world map and the global systems we depend on. As the fragments of Laurasia and Gondwana continued their slow drift across the globe, Earth gradually transitioned into the configuration we recognize today. This settling of continents into modern positions was not quick. It took tens of millions of years, with tectonic collisions, rifting, and shifting oceans guiding the process. By the end of the Cenozoic era, the continents had largely assumed their current shapes, though they are still in motion even now. One of the most dramatic events in this transition was India's collision with Asia. Having broken away from Gondwana around 130 million years ago, India raced northward at unprecedented speeds. Around 50 million years ago, it slammed into Asia, crumpling the crust and raising the Himalayas. This mountain range, still rising today, is the tallest on Earth, a living monument to tectonic collision. The uplift also intensified monsoon systems, reshaping the climate of Asia and influencing life across the region. Africa, too, drifted northward, eventually colliding with Europe. This slow-motion crash helped close parts of the ancient Tethys Ocean and uplifted ranges such as the Alps. At the same time, the Mediterranean Sea was born as a remnant of the Tethys, caught between converging plates. Around 6 million years ago, during the Messinian salinity crisis, the Mediterranean nearly dried out completely before being refilled by Atlantic waters in a cataclysmic flood. South America split from Africa much earlier, opening the South Atlantic. As it drifted westward, the continent eventually collided with smaller tectonic plates along its western edge. These collisions raised the Andes, one of the longest mountain ranges on Earth. The Andes profoundly shaped South America's ecosystems, creating diverse climates from tropical rainforests to arid highlands. The rise of the Andes also altered river systems, eventually giving birth to the vast Amazon basin. Australia's separation from Antarctica was another key step. Around 45 million years ago, Australia broke free and began moving northward. This drift carried it into warmer latitudes, transforming its ecosystems into the unique environments we see today, home to marsupials, eucalyptus forests, and coral reefs like the Great Barrier Reef. Antarctica, meanwhile, became isolated at the South Pole. When the Antarctic circumpolar current formed around 34 million years ago, it locked the continent into a deep freeze, leading to the growth of permanent ice sheets that still dominate its surface. North America, part of Laurasia, also evolved into its present shape. The opening of the North Atlantic separated it from Europe, while tectonic collisions along its western edge built the Rocky Mountains. In the east, ancient mountain ranges like the Appalachians eroded down, while inland seas rose and fell, leaving behind fertile plains. These shifting continents profoundly altered ocean circulation. The closure of the Central American Seaway, when North and South America joined about 3 million years ago, connected the Atlantic and Pacific Oceans only through the Arctic. This event strengthened the Gulf Stream, a current that carries warm water northward and shapes the climate of Europe. Similarly, the opening of the Drake Passage between South America and Antarctica allowed the Antarctic circumpolar current to form, isolating Antarctica in its icy state. The settling of continents also influenced evolution. As landmasses moved apart, species became isolated, evolving independently. This process, called vicariance, created unique ecosystems. Marsupials thrived in Australia, while South America developed giant ground sloths and terror birds. Africa's ecosystems gave rise to early hominins, ancestors of humans, who eventually spread across the globe. The modern distribution of species is deeply tied to this tectonic history. By the time humans appeared around 300,000 years ago, the continents had reached positions very close to what we see today. Their coast mountains and climates provided the stage on which civilizations would rise. Yet the story is not finished. Continents continue to drift at rates of centimeters per year. In the far future, new collisions and rifts will reshape the map again. As you drift into rest, imagine Earth during this transition. Mountains rising where continents collide, new oceans opening as land pulls apart, forests and deserts shifting with changing climates. Picture Antarctica slipping into its icy isolation, India crashing into Asia, and South America colliding with oceanic plates to raise the Andes. Slowly, patiently, Earth sculpted itself into the world we know. In the next chapter, we will explore how the rise and fall of supercontinents influenced Earth's climate over deep time, shaping ice ages, greenhouse periods, and the environments in which life evolved. Supercontinents were not just geological formations, they were climate engines. The rise and fall of these massive landmasses profoundly influenced Earth's atmosphere, ocean currents, and even the long-term balance of greenhouse gases. Climate, in turn, shaped ecosystems, steered evolution, and determined the fate of entire lineages of life. To understand ancient climates is to see how intimately geology and atmosphere are intertwined. When continents cluster into a supercontinent, the climate becomes extreme. Vast inland regions lie far from the moderating influence of oceans. Without seas to regulate temperatures, summers become scorching and winters bitterly cold. Rain struggles to reach these interiors, creating immense deserts. Evidence from the time of Pangaea shows vast arid zones stretching across its heart. Sand dunes and red beds preserved in rocks speak of parched landscapes, while fossilized plants and animals reveal adaptations to dry, seasonal extremes. At the same time, supercontinents disrupt ocean circulation. Normally, currents distribute heat around the globe, keeping climates relatively stable. But when continents block ocean pathways, currents weaken or reroute, altering heat flow. During the time of Pangaea, for example, the superocean Panthalassa dominated, but circulation within it was sluggish compared to today's more fragmented seas. This uneven heat distribution contributed to climate instability, with alternating wet and dry periods across much of the globe. Volcanism also played a role. As supercontinents assemble, subduction zones along their edges often fuel massive volcanic activity. This volcanism pumps carbon dioxide into the atmosphere, triggering greenhouse conditions. Conversely, when supercontinents begin to break apart, new rift zones expose fresh rock, which chemically weathers and draws carbon dioxide out of the air. This process, called silicate weathering, can cool the planet dramatically. Thus, the tectonic life cycle of supercontinents directly connects to Earth's long-term carbon cycle. One of the most dramatic examples occurred during the breakup of Rodinia around 750 million years ago. Intense weathering of rifted rocks may have drawn down enough carbon dioxide to plunge the planet into a snowball Earth state when ice sheets spread nearly to the equator. Life barely survived these glaciations, but their aftermath may have paved the way for the rise of complex organisms. In this sense, supercontinents not only influenced climate, but also set evolutionary thresholds. Pangaea also left its climate signature. Fossil evidence suggests that during its reign, monsoons swept across its coasts, driven by strong seasonal contrasts between ocean and land. Gigantic swampy forests thrived in wetter regions, laying down the coal beds we mine today. Meanwhile, the interior deserts baked under relentless sun. This patchwork of climates influenced the distribution of dinosaurs, amphibians, and early reptiles, forcing species to adapt to extreme conditions or perish. The positioning of supercontinents relative to the poles further shaped climate. When large landmasses drifted over polar regions, they allowed ice sheets to expand. This not only cooled the planet but also reflected sunlight, reinforcing glaciations. Conversely, when continents clustered near the equator, less ice formed, and the planet warmed. For example, during much of the Mesozoic era, with Pangaea straddling the equator, Earth was locked in a greenhouse state. Tropical forests spread widely, and even the poles were ice-free. As supercontinents break apart, ocean gateways open. These new seaways allow currents to circulate more freely, redistributing heat across the globe. The opening of the Atlantic Ocean after Pangaea's breakup, for instance, created currents like the Gulf Stream, which carried warmth northward and made Europe's climate milder. Such changes in circulation helped shape the rise of new ecosystems and influenced the evolutionary path of mammals and birds. The lesson of supercontinents is clear. Climate is not just about the sun or the atmosphere. It is about geology. The arrangement of continents, the presence of mountain ranges, and the opening or closing of seaways can tip the balance between greenhouse warmth and icy ages. Earth's history shows repeated swings between extremes, and supercontinents were at the heart of many of these transformations. As you imagine these ancient worlds, picture the vast deserts of central Pangaea, the swampy coal forests of its wetter edges, and the icy grip of snowball Earth after Rodinia's breakup. Picture monsoons lashing coastlines, volcanoes belching carbon dioxide, and shifting currents carrying warmth to new regions. Climate was not static. It was alive, sculpted by the restless motions of land and sea. In the next chapter, we will turn from climate to life itself, exploring how the rise and fall of supercontinents shaped evolution, driving both mass extinctions and bursts of diversity across deep time. Life has always been bound to the shifting face of Earth. The rise and fall of supercontinents were not just geological events, they were biological turning points. Each assembly and breakup reshaped ecosystems, opened new pathways for migration, and closed others forever. Supercontinents determined where species lived, how they evolved, and even whether they survived at all. To study the history of life is to see the imprint of supercontinents etched into evolution's path. When continents merge into a supercontinent, ecosystems collide. Plants and animals that once evolved in isolation suddenly meet. This can spark evolutionary innovation as species compete, adapt, or merge into new niches. But it can also trigger extinction as dominant species outcompete weaker ones. The formation of Pangaea is a clear example. Before it assembled, diverse ecosystems thrived separately on Gondwana, Laurasia, and other landmasses. Once joined, many species spread widely, but others disappeared, unable to cope with the new competition and harsher interior climates. Isolation is equally important. When supercontinents break apart, populations are split by new oceans, drifting into evolutionary separation. Over millions of years, this isolation drives divergence, producing new species adapted to different environments. The breakup of Pangaea during the Mesozoic created the conditions for the great radiation of dinosaurs, mammals, and flowering plants. As continents drifted apart, lineages diversified, filling ecological roles across the globe. Supercontinents also shape the seas. When landmasses cluster, shallow coastal areas shrink, reducing the environments where marine life often thrives. Much of the biodiversity of oceans comes from continental shelves. Broad, shallow seas rich in nutrients and sunlight. During supercontinent assemblies, these habitats contract, leading to declines in marine diversity. Conversely, during breakups, new coastlines expand the shelves, creating fresh space for coral reefs, fish, and other marine organisms to flourish. The assembly of Pangaea coincided with one of the greatest biological crises in Earth's history, the Permian-Triassic extinction, about 252 million years ago. Sometimes called the Great Dying, it wiped out more than 90% of marine species and 70% of terrestrial vertebrates. While many factors contributed, including massive volcanism and climate change, the assembly of Pangaea played a role. The loss of shallow seas, the spread of deserts, and the disruption of habitats all compounded the stresses life faced. It was a stark reminder that geology and biology are inseparable. But just as supercontinents brought destruction, they also paved the way for renewal. After the Great Dying, life rebounded. Dinosaurs rose to dominance in the Triassic, filling niches left empty. In the oceans, new groups of reptiles, mollusks, and fish radiated into fresh habitats created by shifting seas. The cycle of extinction and diversification repeated with each tectonic upheaval, shaping the evolutionary tree. Earlier supercontinents also left their mark. During Rodinia, roughly 1.1 billion years ago, life was still microbial. Yet even then, the assembly and breakup of continents influenced evolution. The snowball Earth glaciations that followed Rodinia's breakup stressed early ecosystems, but may have spurred the rise of multicellularity. Harsh conditions selected for organisms that could cooperate, paving the way for more complex forms. In this sense, supercontinent cycles may have been catalysts for life's greatest transitions. Migration patterns were another consequence. When Pangaea formed, animals like early reptiles could spread across vast distances. Fossils of the same species have been found on multiple continents, evidence of once unified habitats. Later, as continents split, these lineages became isolated. Marsupials, for instance, spread across Gondwana, but when it fragmented, they became confined to Australia and South America, evolving in unique ways. Continental drift turned once shared lineages into globally distinct ecosystems. Plants were equally affected. The vast coal forests of the Carboniferous thrived when continents were humid and swampy. But when Pangaea assembled, arid conditions spread, forcing plant lineages to adapt to drought. Later, as climates shifted again, flowering plants emerged, reshaping ecosystems and co-evolving with insects. Supercontinent cycles continually press life to innovate, adapt, and expand into new forms. The pattern is clear: assembly narrows habitats, reduces biodiversity, and sometimes triggers extinction. Breakup expands habitats, encourages diversification, and fosters innovation. It is a rhythm of contraction and expansion, destruction and renewal, written into the fossil record. As you imagine these ancient worlds, picture trilobites vanishing as shallow seas disappeared, then picture new fish and reptiles rising in their place. Picture swampy forests giving way to deserts, then returning as continents split and climates shifted. Picture dinosaurs spreading across Pangaea, then diversifying into new forms as the continents drifted apart. Evolution was never separate from geology, it was sculpted by it. In the next chapter, we will explore how the breakup of supercontinents shaped the oceans themselves, altering currents, chemistry, and habitats, and setting the stage for entire eras of marine life. When continents split apart, the oceans respond. The breakup of a supercontinent is not simply the rearrangement of land. It is the birth of new seas, the redirection of currents, and the reshaping of marine environments across the globe. Water and land are partners in Earth's dance, and every tectonic shift ripples into the oceans, altering their chemistry, circulation, and ecosystems. Imagine the moment when a great landmass begins to rift. At first, cracks form in the crust, filled by lakes and narrow seas. Over millions of years, these widen into full oceans. The Atlantic Ocean, for example, was born this way when Pangaea began to split around 180 million years ago. What is now a vast body of water began as a rift valley, then a narrow seaway, and finally an expanding ocean basin. Such beginnings have played out repeatedly across Earth's history, each time reshaping the map of the seas. As new oceans form, they create fresh coastlines. These shallow waters, bathed in sunlight and rich in nutrients, become hotspots of marine life. Coral reefs, shellfish, and fish flourish along these margins. The expansion of coastlines increases biodiversity, providing countless new habitats. The breakup of Pangaea led to an explosion of shallow seas, supporting the radiation of marine reptiles, ammonites, and the ancestors of modern fish. Where once there was a single vast interior ocean, there were now many smaller, dynamic seas teeming with life. Ocean circulation also changes when supercontinents break apart. Currents depend on the shape of ocean basins and the placement of continents. When landmasses cluster together, circulation is limited, and interiors can grow stagnant. But when continents scatter, currents weave through new pathways, distributing heat and nutrients more widely. The breakup of Rodinia, for instance, may have disrupted circulation in ways that contributed to global glaciations. Similarly, the opening of the Atlantic reshaped currents that drive modern climate, such as the Gulf Stream. Chemistry shifts as well. New mid-ocean ridges release heat and minerals, altering seawater composition. When continents split, volcanic activity often surges, pumping carbon dioxide into the atmosphere and nutrients into the oceans. These changes ripple through ecosystems, sometimes fostering blooms of life, and at other times contributing to crisis. The breakup of Pangaea was linked to massive volcanic eruptions that both warmed the climate and acidified the seas, challenging marine organisms but also driving evolutionary turnover. For marine ecosystems, breakups are double-edged. On one hand, they create new habitats and opportunities. On the other, they can destabilize environments. Rapid changes in temperature, chemistry, or circulation can stress species, leading to extinctions. Yet life is resilient. Each breakup has sparked new waves of diversification. As survivors adapted to altered seas, the story of marine evolution is inseparable from these cycles of destruction and renewal. Breakups also influence long-term climate. When continents drift apart, they expose more coastlines where chemical weathering draws carbon dioxide out of the atmosphere, cooling the planet. They also change ocean gateways, altering the transport of heat from equator to poles. These shifts could trigger ice ages or warm periods, amplifying the role of oceans as climate regulators. The fragmentation of Rodinia, for example, is thought to have played a role in the onset of snowball Earth, when oceans froze almost entirely. The geography of oceans shapes the geography of life. Consider Gondwana's breakup, which gave rise to the Indian Ocean. This new body of water redirected monsoon systems, influenced African climates, and eventually created the conditions for the rise of human civilizations along its coasts. Oceans born of tectonic rifts are not just geological features, they are cradles of culture and evolution. In the grand cycle, oceans expand and contract just as continents do. The Atlantic, still widening today, will one day shrink as another supercontinent assembles. The Pacific, vast and ancient, is slowly closing, its fate sealed in the subduction zones along its edges. Oceans live and die on geologic timescales, always tied to the restless movement of continents. As you drift into rest, imagine Earth from above. Watch as a great continent cracks, narrow seas form, and over millions of years, they widen into blue expanses. Picture currents weaving new patterns across the globe, carrying warmth, nutrients, and life. Picture coastlines lengthening, shallow waters sparkling with coral reefs and fish. The breakup of supercontinents is the birth of oceans, each one carrying new possibilities for life. In the next chapter, we will step back from the oceans and look deeper into the engine that drives all these changes. The science of plate tectonics, the invisible force beneath our feet that shapes continents, oceans, and the very face of the planet. Beneath our feet lies the engine of Earth's endless transformation. It is a force so steady and so vast that we rarely notice it, yet it has sculpted mountains, opened oceans, and created the cycle of supercontinents. This force is plate tectonics, the slow, constant movement of Earth's outer shell. Without it, supercontinents would never have formed, oceans would never have shifted, and the planet would not be the restless, living world we know today. The story begins with Earth's structure. The outermost layer, the crust, is not one unbroken sheet, but a mosaic of plates. These plates float on the mantle, a deeper layer of hot, slowly flowing rock. Heat from Earth's interior drives convection currents in the mantle, much like water simmering in a pot. These currents push and pull the plates above, setting them into motion. Though they move only a few centimeters per year, over millions of years they reshape the entire surface of the planet. Plate tectonics explains why continents drift. When plates diverge, new crust forms at mid-ocean ridges, where magma rises and cools. When plates converge, one may sink beneath another in subduction zones, recycling crust into the mantle. Where they grind past one another, faults form, triggering earthquakes. This constant recycling and reshaping is the foundation of the supercontinent cycle. The assembly of a supercontinent begins when drifting continents converge. Over tens or hundreds of millions of years, plates carry landmasses together until they collide. These collisions form towering mountain ranges, like the Himalayas today, where India continues to crash into Asia. In ancient times, the collisions that created Rodinia, Pangaea, and other supercontinents built mountain belts, now worn into the roots of continents. Each supercontinent bears the scars of its assembly in these ancient rocks. But plate tectonics does not stop once a supercontinent forms. Heat builds beneath the vast landmass, unable to escape easily through its thick crust. Eventually, this heat weakens the lithosphere, leading to rifting. Cracks form, splitting the supercontinent apart. Volcanic eruptions accompany the rifting, and new oceans open where the land once joined. Thus, the same process that builds supercontinents also ensures their destruction. The cycle is endless. Assembly followed by breakup, balance followed by change. Tectonics also shapes climate. The positions of continents influence ocean currents and atmospheric circulation. When continents cluster near the equator, they absorb more sunlight, warming the planet. When they drift toward the poles, ice sheets can grow, reflecting sunlight and cooling the earth. Mountain ranges created by tectonic collisions also affect climate, redirecting winds and rainfall. The uplift of the Himalayas and Tibetan Plateau, for instance, transformed Asian monsoons and accelerated the drawdown of carbon dioxide through rock weathering. These changes ripple into global systems, tying geology directly to climate stability. Even life is influenced by plate tectonics. The recycling of oceanic crust at subduction zones drives volcanism, which releases gases into the atmosphere. This process maintains the balance of carbon dioxide and oxygen that life depends on. Without tectonics, Earth's atmosphere could have grown stagnant, like Venus, or too thin, like Mars. By keeping the carbon cycle active, tectonics has been a quiet guardian of habitability. The evidence for plate tectonics is written into Earth's rocks. Matching fossils found on distant continents show that lands, now separated by oceans, were once joined. Mountain ranges on different continents line up, as if once connected. Magnetic stripes frozen in seafloor rocks reveal how oceans have widened. Taken together, these clues confirm the restless drift of continents across time. As you imagine this process, picture the crust beneath you moving silently, too slow to notice yet powerful enough to shape worlds. Picture continents drifting like rafts on a vast mantle sea, colliding to form mountains, splitting to birth oceans. Picture the deep interior of Earth, hot and convecting, churning endlessly to drive the surface above. This unseen force is the heartbeat of the planet, guiding the rhythm of supercontinents. In the next chapter, we will look forward, turning from the past to the future. What lies ahead for Earth's continents? Will they one day join again into a new supercontinent? Scientists have proposed several scenarios, and each paints a different picture of Earth millions of years from now. The future of Earth's continents is already written in the slow but steady drift of tectonic plates. Though we may not see it in our lifetimes, the continents are always on the move, destined to gather again into a new supercontinent. The question is not whether this will happen, but when and how. Scientists have proposed several scenarios for Earth's next supercontinent, each shaped by the directions and speeds of tectonic motion. They carry names like Amasia, Aurica, and Nova Pangaea, visions of Earth hundreds of millions of years into the future. One possibility is Amasia, a supercontinent that would form in the far north. In this scenario, the continents gradually drift toward the Arctic, closing the Pacific Ocean in the process. Asia and North America, already inching closer across the Bering Strait, would collide, followed by Europe and eventually Africa. Over time, South America and Australia would join as well, creating a vast landmass circling the North Pole. Amasia would transform Earth's climate, concentrating land at high latitudes, likely leading to extensive ice sheets and a cooler world overall. Another vision is Aurica, a supercontinent that could form near the equator. Here, the Atlantic and Pacific both close, and the continents come together roughly where present-day Africa lies. This arrangement would place much of the land in tropical regions, creating hot, humid climates across much of the supercontinent. Rainforests, deserts, and monsoon systems would dominate, and life would adapt to an Earth whose land was gathered in the heat of the middle latitudes. A third scenario is Nova Pangaea, sometimes called the New Pangaea. In this vision, the Atlantic Ocean continues to widen while the Pacific steadily shrinks. Eventually, the Americas crash into Asia, closing the Pacific entirely. Europe and Africa follow, until nearly all the continents unite once more. Nova Pangaea would resemble the original Pangaea, with one vast landmass surrounded by a global ocean, reshaping currents, winds, and ecosystems on a grand scale. There are other possibilities too. Some scientists imagine Pangaea Ultima, where the continents reunite in a configuration similar to the past. Others suggest that mantle plumes or unpredictable shifts in subduction zones could lead to entirely unexpected arrangements. While models vary, the constant is the inevitability. The continents will not stay scattered forever. They will meet again, repeating the cycle as they have for billions of years. What would life be like on these future worlds? A supercontinent gathered at the equator might produce extreme monsoons and vast deserts, challenging species to adapt to heat and drought. A supercontinent at the poles might plunge Earth into long ice ages, testing life's ability to endure cold. The placement of land affects ocean circulation too, altering nutrient flows and oxygen levels that marine life depends on. Just as past supercontinents shaped evolution, future ones will guide the path of species yet to come. Climate would also be reshaped. With fewer coastlines, rainfall would be unevenly distributed, leaving some regions parched while others flood. The vast interiors of supercontinents tend to become dry, with harsh deserts far from the moderating influence of oceans. At the same time, mountain ranges formed by collisions would alter wind and precipitation, creating pockets of varied climate across the landmass. Earth would be both unified and diverse, a single continent with many contrasting environments. For humanity, if it still exists in hundreds of millions of years, a new supercontinent would be both a challenge and an opportunity. Resources would shift, coastlines would vanish, and ecosystems would reorganize. Civilizations might rise and fall in response to the changing face of the planet. Yet for all its disruption, the assembly of a new supercontinent would simply be the next chapter in Earth's ongoing story, one written by forces far older than life itself. As you rest, imagine the slow drift of continents over the next 200 million years. Picture the Atlantic narrowing, the Pacific closing, or the Arctic filling with land. Imagine mountain ranges rising where oceans now lie, and deserts spreading where forests once grew. Imagine a new supercontinent, whether Amasia Aurica or Nova Pangaea, spanning the globe, a fresh canvas for the oceans, the atmosphere, and life. In the next chapter, we will explore how supercontinents have always been tied to the carbon cycle and the movement of water, influencing Earth's climate stability and even the survival of life across deep time. Supercontinents are not only landmarks of geology, they are regulators of Earth's climate and life support systems. Each time the continents gather or disperse, they influence the cycling of carbon and water, two elements that govern habitability. To understand Earth's past, present, and future, we must see how the rise and fall of supercontinents connect directly to these great cycles. The carbon cycle is Earth's thermostat. Carbon dioxide Keol in the atmosphere traps heat, keeping the planet warm enough for life. But the levels of Keol are not fixed. They are shaped by geology. Plate tectonics, mountain building, and supercontinents all play roles in balancing the system. When continents collide to form a supercontinent, new mountain ranges rise. These highlands are subject to intense weathering. Rainwater carrying dissolved cal reacts with rocks and pulls carbon out of the atmosphere. Over millions of years, this process lowers cal levels, cooling the climate. The assembly of Pangaea illustrates this effect. As massive mountain chains formed during its collisions, chemical weathering increased, drawing down atmospheric sul. The result was global cooling, which contributed to shifting climates and the spread of arid interiors. The supercontinent acted as both a shaper of land and a regulator of air, linking geology to atmosphere in one grand cycle. On the other hand, when supercontinents break apart, volcanic activity surges, mid-ocean ridges expand, and rift zones erupt with lava, releasing large amounts of cal back into the atmosphere. This influx of greenhouse gases warms the planet, creating conditions very different from those of supercontinent stability. The breakup of Pangaea, for example, was accompanied by enormous volcanic eruptions, known as the Central Atlantic Magmatic Province. These outpourings of lava released enough cal to trigger global warming and contributed to mass extinctions. The cycle of assembly and breakup thus acts as a pump, alternately cooling and warming the planet. Water is equally bound to these tectonic rhythms. Supercontinents influence the water cycle by shaping rainfall, evaporation, and ocean circulation. When land masses cluster, vast interiors grow dry, with little rain reaching far from the coasts. Rivers shrink and lakes may vanish, while coastal regions face intense storms. Conversely, when continents break apart, coastlines multiply, rainfall patterns diversify, and rivers carve new landscapes. Each shift changes how water flows across Earth's surface, nourishing or straining ecosystems. At a deeper level, water also cycles between Earth's surface and interior through plate tectonics. Subduction zones drag water, rich minerals into the mantle, while volcanoes release water vapor back into the atmosphere. This hidden exchange maintains the balance of oceans over geologic time. Without it, Earth could have lost its seas to space or drowned beneath runaway floods. Supercontinent cycles, by driving subduction and volcanism, help regulate this exchange. Together, carbon and water cycles interact. Cooling from cal drawdown can trigger ice ages, locking water into glaciers. Warming from volcanic outgassing can melt ice and expand oceans. Supercontinents act as the stage upon which these feedbacks play out, sometimes stabilizing the climate, other times pushing it into upheaval. The snowball Earth events after Rodinia's breakup and the hothouse climates following Pangaea's rifting both highlight the dramatic consequences of these links. These cycles remind us that supercontinents are more than static landforms. They are active players in Earth's system, connecting deep geology to atmosphere, oceans, and life. Without them, Earth's climate might have swung too far toward the extremes, or grown stagnant and unchanging. Their rhythm of assembly and dispersal has kept the planet dynamic, sometimes harsh, but always renewing. As you picture this balance, imagine rain falling on mountain ranges, carrying carbon into the seas. Imagine volcanoes erupting as continents split, sending clouds of gas into the sky. Imagine glaciers advancing and retreating, oceans rising and falling, forests spreading and shrinking, all connected to the movement of continents across the face of Earth. In the next chapter, we will lift our gaze beyond Earth to ask whether supercontinents exist elsewhere in the universe. Could the cycles that shape our planet also unfold on exoplanets, and what would that mean for their habitability? When we look beyond Earth, the idea of supercontinents takes on a new significance. If continents on our planet have risen and fallen in cycles, shaping oceans, climates, and life itself, could the same process unfold on distant worlds? The search for exoplanets, planets orbiting stars far beyond our sun, has revealed thousands of candidates. Many of them are rocky, some may lie in habitable zones, and a few may even hold water. But for a world to sustain life over billions of years, it may need more than just oceans and air. It may need tectonic activity, and perhaps even supercontinents. On Earth, the supercontinent cycle is tied to plate tectonics, the slow motion of the crust driven by mantle convection. Without this process, continents would not drift, collide, or break apart. The carbon cycle would stall, oceans might shrink or vanish, and climates could swing to extremes. This raises a fascinating question: is plate tectonics unique to Earth, or do other planets experience it as well? Some exoplanets are called super-Earths, larger and more massive than our own planet. In theory, their size and heat might make them more likely to sustain tectonic motion. With stronger convection currents and thinner lithospheres relative to their mass, they could be even more geologically active than Earth. If so, they might have supercontinents forming and breaking apart on faster cycles, reshaping climates and creating conditions for dynamic evolution. On the other hand, tectonics is not guaranteed. Venus, though similar to Earth in size and composition, lacks plate tectonics. Its crust is a stagnant lid, unable to recycle itself efficiently. Without tectonics, Venus's carbon dioxide built up unchecked, leading to a runaway greenhouse effect. Mars, smaller than Earth, once showed signs of volcanism and water, but its interior cooled, shutting down tectonic activity and leaving its surface frozen and still. These examples remind us that even in our solar system, Earth is exceptional. If exoplanets do host tectonics, their supercontinents would influence habitability in ways similar to Earth. They would regulate carbon dioxide, maintain oceans, and foster biodiversity through cycles of assembly and breakup. The presence of supercontinents could be one of the keys to long-term habitability, ensuring not just that life arises, but that it endures. Astronomers cannot yet see supercontinents directly on exoplanets, but they can search for signs of tectonic processes. Variations in atmospheric gases, such as fluctuating carbon dioxide or volcanic sulfur compounds, could hint at active geology. Future telescopes may be able to detect these fingerprints, offering indirect evidence of continents in motion. Some models even suggest that the distribution of land and ocean could influence the overall reflectivity or albedo of a planet, which might one day be measured. The idea of alien supercontinents also sparks the imagination. Picture a world larger than Earth, with continents gathering and scattering every 100 million years. Picture oceans opening and closing, climates shifting between ice ages and hothouses, and life adapting in response. Perhaps advanced civilizations, if they exist, might study their own tectonic cycles, just as we study ours, recognizing the same rhythm of creation and destruction written into their geology. The search for supercontinents beyond Earth is also a search for ourselves. By studying other worlds, we learn what makes Earth rare and what might be common. If we find that tectonics and supercontinents exist elsewhere, it suggests that the conditions for long-term habitability may not be unique. If we find that Earth is alone in this respect, it underscores just how fragile and precious our planet is. As you drift into rest, imagine distant planets circling faraway stars. Some are scorched, some frozen, some cloaked in thick atmospheres. But perhaps on a few continents drift and collide, mountains rise and oceans form and vanish. Perhaps on some distant shore, another being gazes at their skies, wondering about the cycle of continents, the rhythm of oceans, and whether life elsewhere shares the same story. In the final chapter, we will return home, drawing together the